Right, good evening. How are you? Great. Doesn't sound great. First day of semester. How's everybody doing? Starting. So everybody's in W here, right? Computer. Computer. Same thing. Yeah. So W are all computer, NWs. So this is CBS. Engineering Science 3230. This is not the class, then you're in the right class. So what is CBS? What do we learn in this class? What is your preconception about this class?
I've got one. I'm concerned that is the technology of the microcontroller we're going to be learning about relevant? I mean, with Arduinos and stuff that you can write in something that's very similar to C, and now we're learning to use a microcontroller that needs to be programmed in machine language.
See, you are an engineer, right? If you haven't noticed, the class is called computer-based systems. It is not called microchip controllers. It's not called Arduino controllers. It's not called anything else. It's called computer-based systems.
So are they different? I mean, I really don't. That's what I was.
So we're learning the concept that you use to solve problems with these microcontrollers. So there is an architecture that we use in this class that you use to learn the concepts. The idea is, if you get this concept down, if your employer, for example, say, hey, use a microcontroller to actually solve this problem, it should take you a few days to just pick up the microcontroller with the data sheet and start programming and solving problems. That's something you have to keep in mind. All right? And the class project, you actually have to research other microcontrollers and use it to solve the problem that we will give you during the semester. So the idea is you're not learning a specific microcontroller. You're learning the concepts using this microcontroller. Cool? Please keep that in mind. This is very important. Computer systems are a very wide field, and this is just the beginning. What is your first exposure to computers before this? You've been using computers all your life, probably, right? So now you're going deeper level to see what's going on underneath all the abstraction that's hidden from you, because you are engineers, right? So you want to take the full advantage of what computer can do for you. So basically, CBS is an engineer's take to computing. Computers are used everywhere, right? Is that true? So what is your take on computing? What do you want to use this computing power for? Anybody?
Make some money.
Make some money, sure. Anything more specific?
Control the process.
Control processes, right? Without computers, what would be your alternative?
Doing it ourselves.
Mechanical systems. There are many things that are easier to solve with computers. Do you agree? Right. You will also study systems that use computer to accomplish their task. Right. So it's computer-based systems. You will learn about computers to see how they work and then apply them to actual systems. Does that make sense? And in the end, of course, the lifeblood of an engineer is solving problems, practical problems. Right? So you have something that you need to be solved, and then you have to use everything that you've learned in your schooling to solve it. The thing that you have to keep in mind when you go to work, like the problems will probably be something that nobody has solved before. Right? There is no answer on the back of the textbook. Right? Do you agree? So you have to formulate a problem and make sure it works. Well, there could be solutions from previous engineers that may fit to your problem, or you may have to modify their solution to make it fit. But in the end, you are the creative mind. You have to drive that, right? So just by learning how computing works, the basics, it will make you a better programmer. All of you taken a programming class. It's a prerequisite, right? What did you use to program?
Software, IDE,
Whatever. What did you use?
Visual Studio, Electron,
What language?
C,
C?
Visual, yeah, that's the times from C.
So you've learned how to program in C. How about other people? Have you used anything else?
C Sharp.
C Sharp?
C++.
C++? Java? So you've all programmed. Right? You know what a variable is in a high level concept. You know what control structures are. You've seen loops. You've seen if else. You've seen switch statements. Right? Have you ever thought, how does this code get executed on the computer? What happens? What actually happens when you compile your program? Have you ever thought about that? Turn into a machine language, then what? Where's the machine language stored?
Ons and offs for a trillion transistors.
Yes. There's just this abstract idea of how it works, right? You have billions of transistors, but how is it that organized to actually execute your program? So this is the first step when you go lower level. Just by learning the machine language of an architecture will give you an idea of how that layer between the programmer and the computer works. Right? Next, you will also learn about computer interfaces. How do you interface with the computer? Like what?
Keyboard, mouse.
Keyboard, mouse. How does this computer communicate with the keyboard?
Communication bus, like the USB or serial.
USB, right? Is there any other bus that the computers use to talk to anything? A lot of them.
Yes.
We've been talking about high-level computers. What about computers that drive your toaster or microwave, or microcontroller? How does it interface with all those buttons, timers, the magnetrons? Right? How does it do it? So in the class, we also learn about what computer interfaces you'll see. But before we begin, let's go over some administrative details. My name is Mira. I haven't said my name, I just realized. I'm a graduate student in OSU Stillwater in computer engineering. The class website is here. So wmulia.org is my website. And everything will be up here. All the video recording, lectures, etc. We will use OC for submission purposes and grade keeping. Right? So when I need something submitted, it will be through the OC Dropbox. Is everybody familiar with OC? If not, just let me know and we can work something out. It's my email. Please read the syllabus. It's on the website. So it details everything. The class structure, the grading policies, due dates. So it's all there. Please make sure you read it carefully, twice at least, so you know what my expectations are. Homework is due before the class, so we can discuss it. So please do your homework. It sucks to come into class and try to bring up a discussion where nobody has at least attempted before. Right? At least attempted homework so we can get a discussion going, if there's a homework. So labs are due by the end of the session, if it's due that day. But I don't like to force people to work on my schedule. So if you still need more time and want to spend part of your weekend to finish the lab, please do so. So spend the Friday or Saturday to finish the lab. I grade everything by Sunday. If you still need more time for the specific lab, please let me know. It's okay, right? But just be sure that the extra time you spend is productive. Because if you don't, then it runs toward the next lab and everything gets pushed back. Right? So 3 days of extra time is okay, but if you need more for some extraordinary circumstances, let us know. Cool? Any questions so far? Sounds fair? Structure. There will be approximately 26 lectures. There is no participation grade. You're all adults. I should be able to trust you. But please come, because face-to-face, I think, is the best way to actually learn. If you have a question, I can answer it directly. Although we have Google Hangouts going every Monday and Wednesday. So if you miss it and you have to be somewhere and you're online, you can join the Google Hangout. I also archive the lectures on YouTube, and I'll put it up on the website after every lecture. So if you missed it or you have to review, it'll be up there. Cool? Homework and quizzes, yeah. 5 lab assignments, hands-on. So this is where you actually learn. All right, so we have a PLP CPU that we use, and I'll introduce later, where you actually work out concepts and problems. So we'll do this in the labs. And you can also do it if you have a laptop or a computer. You can install this software yourself and do it that way. There are 2 midterms, sorry, and 1 class-wide project. So it's 2,000 points with 1,000 points possible bonus. But it's a bonus. I only give bonus if you go way above and beyond. So do not expect the bonus to be just like real game. So it's actual. And then I have a personal reflections. What we found is that when you learn, you're just not learning the concepts. While you go through the education, you want to be able to learn how you learn, if that makes sense. Right? And sometimes we just go through the motions and we just don't really have a good habit of learning. So in the reflections, there will be some prompts that you have to reflect on what you learned, how you learned, and what you can do to improve, or what I can do to improve your learning experience. Right? Because there are things in this, when you go through your college degree, things that you learn and will never use it again. Right? Is it useless? Probably. It could be a useless thing, but knowing how you learn best is a really good skill to have. You agree? Many skills could be obsolete. Knowing how to learn best will never be obsolete. Stay clear. And this is a good philosophy to have as you expand your horizon and develop as a person. So to get an A this class, you need to get over 9,000 points. Right? So there are 12,000 possible points, including the bonus. So if you add this up, it will be 11,000. If you get more than 9,000, you get an A. Right? So you have 20% grade just for the A. And there will be no curves. So whatever you get is what you get. Any question on grading? No? Sounds fair? Any concerns? Not yet. We'll think later. Cool? Ready to start? Well, so this class is also part of a research project for a computer engineering education. So it's what my advisor and I started a few years ago. So the website is over there, so if you want to look at research materials, all you have to do is just go through the motions and have fun. Hopefully you learn a lot in this class. Cool? So let's start. So we started with computers, right? Let's formalize it. What is a computer? Let's hear some answers. Gentleman in the green shirt, what do you think a computer is?
Something the user uses to make everyday life easier.
Yes. A tool.
At its base.
A system, a tool, right? Anybody else? It's a computer, precious. What is a computer? Have you ever thought about it? How do you define a computer? What does it have?
Memory.
Memory, good answer. One of the 5 blocks. What else?
Processing speed. Or processors.
A processor, something that processes stuff, right? Second block. What else?
I.O.
I/O. 2 blocks and 1 answer. Can somebody give me the 5th element?
Interface.
Close. No, sorry. What connects them together?
Software.
Bus.
Bus. You guys are good. Right? Everybody get that? Those 5 blocks. We'll see that later. So now let's see what Google has to say about what a computer is. I'll do this. Google, what's a computer? Computer. An electronic device. Let's see if I can zoom in. An electronic device for storing and processing data, typically in binary form, according to instructions given it in a variable program. So many buzzwords. What can you pick up from this definition that you think it is interesting? Storing and processing data. We throw that word around so much. What is data? Right? Typically in binary form. According to instructions given to it in a variable program. What makes a computer different than other systems that do some processing? Go wild. Free your mind.
Versatility?
Versatility. Coming from what?
I just thought it was one word.
That's a really good answer, though. A variable program. What does it mean?
It can be programmed.
It can be programmed, right? It's huge.
Software defining hardware.
I need to compute that first. Software defining hardware.
But if you have a bunch of relays connected to your USB port, you can make breakfast
Yes.
defined by the software.
Yeah.
Software defined.
Software defined system, I would say. Right? So being able to be programmed is the primary defining attribute of a computer, right? Because many other things can compute. You have an abacus you can do to actually compute some arithmetic operations, right? But can you do it to develop an algorithm that calculates some Newton's method? No. Can you do it in Java? Easily, right? But what do you want to do like a traveling salesman problem on an abacus? I guess some people will come up with some scheme to be able to do it. But with a program, you just start coding like a maniac for like until 2 a.m. and it solves it, right? How awesome. Computer. So, list of concepts that you need to know. Program. So program is basically a sequence of instructions. So what is an instruction, do you think? What is an instruction to a computer? A what?
Command.
Command. Command to do what?
Specific task.
Specific task. Right? The unique thing about a computer, it only understands a combination of some specific task it can do. Right? And you combine all this task command as a program. And in the program, you can have a lot of things. Algorithms that do a lot of things, right? Compute, find where the eye is on an image. Computer can do that. If the programmer can write the algorithm. Everything, right? So program. Can you do a lot of things with just a program? What do you need? What does a program process? Data. Right? So not just a program. You also need some data that you can process and produce some output data that is useful to us in some way. Does that make sense? Things like simple things. I have all your grades, now I'm on the average. The input data will be a list of grades. The output data will be the single number that represents the average of that class's performance. Cool? So what's the difference between program and data? From the perspective of the CPU.
Data is variable.
It's variable.
Yeah.
Program is a subset of data. But what makes program special? You can what? This is a hard concept to grasp at first. Program is data? You must be kidding me. You'll find out later that the program gets stored the same way like data does.
The program processes the data.
Yes, by being what? By the CPU. Executed.
Execute.
Right. Program is basically just a collection of things on your data that the CPU understands how to execute. Is that clear? On the hard drive, do they share program and data? Yeah, you have program files and you have some My Documents on the same device. Right? So you might be thinking, like, hey, so what's so special about program? It's just .exe. You can double click and the CPU knows how to execute it and trash your computer if it's a virus. Right? So let's go through the blocks. Processor, CPU. We look into this. What is a processor? And you have memory, you have input output, and you have something to connect these together, which are the buses. So let's look at how a CPU executes a program. How do you think a CPU executes a program? Draw from your experience. Remember this morning when you open you power up your desktop and you want to launch Chrome. What actually happens? Or Firefox, whatever, or IE, whatever browser you use. What happens? Tell me a story of how a program gets executed on your desktop. And I'm sure the first program you execute, either an operating system, will be the browser, right? Yeah, don't lie. All right. What happens when you double-click that icon or click that icon?
It calls the program in memory.
Where is the program stored?
Puts it into the RAM.
Yeah, hard drive gets moved to RAM, and from there the CPU can know, like, hey, I have to start executing this list of instructions. Right? Does it make sense? On a really abstract level. Now let's look at a really simple CPU that I've designed last night. Right? We'll have a really simple CPU, and then we'll see how the CPU can do some useful operations, relatively speaking. So, have you ever seen a diagram like this before? This is the first. Yes? I see nods. Who has seen something like this before? Some familiarity with some of the shapes?
I've seen rectangles before.
Nah, you know what I meant, sorry. But it's like this. Have you seen this before? No? Have you heard the word register? What do you think a register does? Stores something. Cache. Stores something, right? So a register is basically just temporary storage space on the CPU. Why do you need this temporary space? Let's see. And then you have something called the arithmetic logic unit. Performs arithmetic operation. So you have these two things. You have two registers and one ALU. What do you think the ALU does? Those arrows give a huge hint. Can you think of what the CPU can do with this structure? Outputs to it. Yeah. All right. So you have two registers. This ALU can read from those registers, do some work, some computation, and write it back to the first register. Make sense? Now, the CPU will also have some control logic that will actually interpret the instructions getting into the CPU. That's how the CPU knows like what to do. Oh, I'm supposed to do this. Next instruction. Oh, I'm supposed to do this, etc. etc. Cool. Now let's create some instructions that this CPU will understand. First, we need to get some value to the CPU for it to do any useful work, right? So we have an instruction that says get a value to register 1. So you provided a value, and the CPU will put that value to register 1. Second one will be get a value to register 2. Does that make sense? Third one, hey, CPU, add the two numbers on the registers and store it in R1. Cool? Now this instruction actually uses the ALU, whereas the first two don't. Is that clear for everybody? So as you can see, different instructions may not use the whole CPU. So there may be some things that the CPU don't use. Oh, some instructions where the parts of the CPU don't get used. The last instruction will be to subtract R2 from R1 and store the result in register 1. 4 instructions. How useful can the CPU be? What sort of operations will you make the CPU do? Any takers?
Find a percentage.
Find a percentage? Kind of hard to think. Sounding will be the simplest thing you can do. Right? Because you don't have comparison, so you can't really do a division. So all this can do is just keep adding or subtracting numbers forever, right? So let's see if this CPU can solve this problem. So you want to add these 3 numbers. How many instructions do you think we will need if we use this CPU? 2? Definitely more than 2. You need at least 2 to get 5, right? Yeah, you need at least 2 to get the values in there. But since you only have 2 registers, you can't have 3 in the same time, right? Does it make sense? Well, let's step through this. So you have, come on, animation. All right, so the first 2 instructions, you will just load this to the first register, load this to the second register, right? Now you have your first 2 operands. What do you do next? Add them together. Now your second register is free, right? Now you can load the third number, and you get your answer. Cool? And that's actually how a CPU executes a program, sequentially. Why do you think it has to do it sequentially?
I can't imagine another way to do it. I mean, how would you keep track of the data asynchronously?
It doesn't have to be sequential. We designed CPUs that do it this way because it makes sense. It's a trade-off. We can have a CPU that actually decodes a C program directly without compiling. But that CPU will be so complex, it's just not worth it. Make sense? You will find that many things in the engineering world are trade-offs of many parameters. You can make some awesome thing that does this thing, but when you look at the cost, it will cost $3 billion. Forget it, right? So a programming language is a compromise between how we read the algorithm and how the CPU or the computer interprets the program. If we program in English, it'll be so ambiguous, the compiler will be so huge and very inefficient. Does it make sense? If we write in machine language, it'll take forever for us to type in all those zeros and ones or flip the switches. So a programming language is a good compromise between our way of thinking and the computer's way of executing or thinking in a few hundred years. Who knows, right? So, any questions so far? No? Is the connection still starting to form between how you program in high-level language and how the machine interprets it? Kinda? Just looking from that expression, this program, you can kind of see what you need to do to make the computer do something, right? Now, there are other questions, right? So things like, where is the program stored? which we kind of talked about before. How is the program stored? This is a deeper question. This is the kind of question that I may ask in midterms, like a deeper level question, not golem level question like before, but things that require you to critically think of how are these things are done. Right? How does the program actually get to the CPU? We talk about buses, but how? How does it know where the program is? How do you design a CPU that can fetch things from memory? All right, so we'll get to that. How does the CPU understand the program? We talked in high level, control logic, but how? It's like, how does the program, the instructions actually get represented when it gets to the CPU? Have you ever thought about that? Is assembly the answer? Who has seen an assembly language program? Two of you. Do you think that is what the CPU sees? No. Assembly is still a compromise between us and the computer. Right? Assembly, even though it's hard to see the flow of the program, you can kind of still see the instructions because it's in Latin alphabets. Right? Add A, B, store C. That makes sense. But when you get to the computer, it's actually still just 0 and 1s. Right? What if I need to save more than 2 numbers on the CPU? How many registers do you think a typical CPU has? This will be a really common answer. Depends. Some CPUs have 32 registers. The x86 that you see, I think it's about from 8 to 16, I don't remember. The Motorola has 4. The Sun Spark has between 64 to 128. Right? And there are trade-offs of why all these different architectures have different number of registers. And usually there are good reasons, like why these certain architectures have this certain number of registers. Any questions so far? Yeah, what if I want to get the input from the user? Right? You don't want to have all your data written on your program. Sometimes you want to wait for a keyboard. How does it work? How do you interface with the keyboard? So at this simple CPU is basically useless. All it does is just add, and there's no way for you to actually enter data, and there's no way for you to actually get data out from it. Does that make sense? What do you think you will need to get data in and out from there? What kind of instructions? Let's think about in terms of instructions. Let's see if somebody can come up with instruction that will allow you to interface with memory. If you are the computer architect, what kind of instruction would you design for it?
An ASCII reader or something?
No, I just want a CPU. You've seen an instruction where you load a number to a register. Inherent, like immediately from the instruction, right? So load number 5 to register 1. That's immediate loading. The other way is to do like a memory load. Load from memory from here, which you'll see later. So that's how you actually get data from the outside of the CPU and outside the program.
Like on the Altair, what is it, that 800 that just had the toggle switches on the front, you had to load each number one at a time. That's kind of what you're
Well, no, 8800, you are basically coding your instructions, right? That's still direct. That's still immediate. You're immediately. It's just like having a constant in your program. That 5, for example, if you have like a constant number 5, a equals 5, that 5 is included in the program, right? So when it compiles it down, all it does is just okay, load 5 to this some register. It doesn't go beyond this, other than just fetching the program. You will see this later. So now, we've got to see how the program executes. We need to see how we can get data from the memory and the I/O devices. Right? So we've talked before that this is how you would organize your computer. So you have your CPU, you have an input device, or a list of input devices, you have memory, you have output devices. And the buses will comprise of address, data, and control. What do you Can you think why we need these three? Why not just data or just address? What do you think an address bus does?
Towards the location of the
Whatever.
bits of data.
Yeah. Location. Right? So on your program, instead of loading the value directly or immediately from the instruction, now you have the option of, hey, I want to get data, but not from you instruction or program, but from there. Now you have some indirection going on. Does it make sense? Now we have a problem. So you have program being stored in memory. You have data being stored in memory. Now people are start feuding. It's like, oh, that's bad, right? Why do we store them in the same place? Why don't we split them? No, we should. So this argument is called the von Neumann versus Harvard architecture. So there are two ways to actually store program and data. You can have a single memory where both program and data share the space. That's von Neumann architecture. Smart guy. And the second paradigm was to separate the program and data on different memory spaces. Can you think of pros and cons for both approaches?
Making the same space be faster to get that data.
It'll be faster. Faster is a very relative term,
True.
right? How so? Will be the next question. Why would having a shared program and data be faster?
Because it would take just one bus from there all the way to that data. It's not using multiple buses.
It'll actually make it, well, if you can assume that both are operating at the same speed, it'll actually be slower, right? Because if you share program and data, now, when you execute a program, you need instruction like every time, right? But sometimes you also need data when you are processing your whatever. So you need a program, you need instructions being fed into your CPU all the time. Then you need data, but you only have one set of buses. Then you have the von Neumann bottleneck. Right? Okay, I get my program. Wait, program come in. Okay, data come in. Right? That's the drawback of having a shared program and data. You don't have that problem with the Harvard architecture. Well, what are the cons for Harvard architecture?
Complexity.
Complexity. Now you need two sets of buses for both program and data. Right? So, but more buses mean more wires. Let's talk about 64-bit CPU. Now you just have, from 64 wires, you get 100 wires. That's a lot of real estate on your silicon, right? Does that make sense? So with von Neumann, you have less wires but less bandwidth, theoretically speaking. And with Harvard, you have more wires but bigger bandwidth. But, as I said before, it's all about trade-offs. Modern processors, at least general purpose ones like on your smartphone or your laptops or your desktop computers, are modified hardware architecture. It's a hybrid. Right? For smaller microcontrollers, it'll probably be Harvard. Right? Because probably simpler to program, or that's how it's designed originally. Cool? Trade-offs, trade-offs, trade-offs. On your own optimal solution. Okay. So, what is this then? Why?
I changed my answer. Harvard.
No.
I say von Neumann because there's only one memory storage.
Yes. And one set of buses, right? You have three buses, but they do all the different things. Right? But yes. So both program and memory will have program and data will have to go to that memory block. Cool? Is it the final answer? No. It could be. It could also be modified. Have you ever heard about computer caches, CPU caches?
Isn't that like the register we were talking about?
No. Register is on the CPU. This is outside the CPU.
L1, L2, L3.
L1, L2, L3. And L1 is usually split.
The largest is small.
No, L1 is the smallest.
Or is it? Is L3 more?
Yeah. So when it's split, it's hardware. But from the CPU and programmer's perspective, it's all one memory. So it's one unit
Those aren't actually on the.
on the silicon. Yeah.
It is on the silicon.
But not on the CPU level. If you want to learn more, take computer architecture, 4243. If you're a C, you have to take 4243. So most modern computers, like general purpose computers, are modified hardware for performance considerations. Now we have memory. We actually need a way to address the memory, right? So how does this work? So the part of a program, part of a computer in which the end of a program instructions can be stored for retrieval. So it's like this pool of storage space where you can have your program there, you have your data there, and another program there. How does the CPU know which ones to execute or which ones to fetch? Addressing, right? So a functional description of a memory, there are two major functions of a memory. You either write to it or you read from it. Or if it's read-only memory, you only read from it, right? There is no write-only memory. That was a joke. Actually, there's like a, back in the 70s, there's this company, I think it's, I forgot what the company was. So they have a catalog that there was no internet, right? So it's a mail order catalog. So they sell components called the write-only memory. They don't, but some engineers think that their Q&A department is slacking. So they have a data sheet that actually describes the write-only memory, which is useless. It looks official with all the graphs and everything, and it got through. And then the sales department started getting inquiries about the device that they finally pulled that catalog back. We don't sell write-only memory. You guys should look it up. It's hilarious. Okay, so there are two functions on a memory. First, if you want to read, you give it an address and then a read control signal, right? And then after a while, you'll get the data back on the data bus. When you want to write, you provide the address, the piece of data, and the write signal. Simple? Well, on a high level, it looks simple. But we need to go down and actually look at how memory is actually addressed. And to do that, we actually have to learn how the CPU, how computer represent data. So next week, we get digital. We learn how digital systems work. Just a quick review of the digital systems. I think in your programming class, you should learn of what bits are, bitwise operations, logic gates, Boolean algebra. You guys remember that? This is an important question because if you guys do remember it, I'll skip it. No, people start shaking now. I remember it. Boolean algebra. What's an AND gate? What does an AND gate do?
It's for two negatives, right? Or two no's.
Two no's equal?
One.
No. And both have to be true. Both inputs have to be true to get that true.
Oh, that's right. Yeah.
But what XOR?
One or the other.
One or the other. Yeah. So you can review this yourself. It's straightforward, right? So let's recap. Tech course website. I put up everything there. So we have 5 minutes left. Attend class. First step to success. I'm awesome. So it's not awesome. Computer and computing systems. Know what computers are and how they work in the system. Program, which is list of instructions and data. We just skim through this a little bit, but we get into more details. But it'll get you to the mindset of how this class will go, right? So you learn the most basic concepts today in such a high level. From here on, from here on, you'll be deeper. So you'll actually start seeing numbers this semester. Too bad. Yes, there are numbers in this class. The good thing about computer engineering, the most complex math you'll see is like a first order algebra. Is that a good thing? No calculus.
Why do we gotta take all these math classes?
Because it's good to know calculus. I would like all well-rounded citizens to know how calculus works. Okay, so we've talked about buses, address, data control. Kinda. We'll go into more details. And then separation of program and data. And why people do it. Any question? Nothing? Like, who the heck is Fritz? Guys. Guess that's it. Any question? Seriously.
Fritz, the other guy with the research program that you're doing?
He used to be my colleague in my lab. He's in San Diego. Just computer. I like that IPA pronunciation. We should switch to that. Computer.
Did you say San Diego?
San Diego. San Diego.
Okay.
Scientist. No question. Not dropping off this class, right? I'll see all of you this Wednesday and Thursday and next Monday, next Wednesday, right?
On the Monday after that.
Labor Day?
Yeah.
Cool. I'll see you Wednesday. I forgot to introduce you my TA. She's online. It's like, where are you? Whatever. You'll see him Thursday. You guys have a good night.